59 earthquakes have hit the same stretch of the San Andreas fault in 6 days, running at nearly 7 times the normal rate for that patch of ground. On Tuesday morning, the sequence produced a magnitude 3.94, the largest event there in almost 15 years. And here is what makes it matter. It is happening on the one section of the San Andreas that is not supposed to break at all. By the end of this video, you will understand why 4 meters of rock pulled from 3 kilometers underground quietly demolished that assumption. The San Andreas fault has been producing earthquakes almost continuously since last Friday. And the place it has been doing it is the one stretch of that fault that geologists have spent decades describing as harmless. The swarm is centered beneath Pinnacles National Park in San Benito County, Central California. It began on Friday, August 7th, with 2 magnitude 3.2 earthquakes about 78 minutes apart. It did not stop. It ran through the weekend, escalated on Tuesday morning, and was still producing events yesterday. In the tightly drawn box that contains the main cluster, the catalogue now holds 59 located earthquakes across 6 days. Nobody has been hurt. Nothing has been damaged. No agency has issued a warning, an advisory, or an elevated alert of any kind, and none of them should have, because on the raw numbers, this sequence is small. The largest event in it would rattle dishes in Hollister and go unnoticed in San Jose. What makes it worth 20 minutes of your time is where it happened. The swarm sits directly on what seismologists call the creeping section of the San Andreas, roughly 150 kilometers of fault running from San Juan Bautista in the northwest down to Parkfield in the southeast. On this stretch, and only on this stretch, the 2 plates slide past each other continuously. They do not stick, build up strain, and release it in a single violent snap. They just move all day, every day, at about the same rate the plate boundary demands. That behavior is the entire reason the standard answer to the question, could the whole San Andreas rupture at once, has always been no. The creeping section has been treated as a permanent barrier, a stretch of fault so lubricated, so incapable of storing energy, that a rupture arriving from the north or the south would run into it and die. Everything you have ever heard about the big one being confined to one half of California or the other rests on that assumption. 4 years ago, a group of researchers pulled rock out of a borehole at the southern end of this segment and found something that does not fit the assumption at all. At 19 minutes and 8 seconds past 10 o'clock Universal Time on Tuesday, August 11th, that is 3:19 in the morning Pacific Time, a magnitude 3.94 earthquake struck 6 kilometers northwest of Pinnacles. The numbers on this one are worth stating precisely because they matter later. Depth, 4.62 kilometers. 85 seismograph stations reported it. The azimuthal gap, a measure of how well those stations surround the epicenter, was 40 degrees, which is good. Horizontal error, 14/100ths of a kilometer. That is not a preliminary automatic solution that might get revised by half magnitude tomorrow. That is a reviewed, well-constrained answer. The fault did exactly this, exactly here. Within 3 minutes and 33 seconds, 3 more located earthquakes followed. A magnitude 2.57, a magnitude 2.60, and a magnitude 2.14, all within a few kilometers. The largest event to follow at any point in the rest of the sequence was a magnitude 2.66, about an hour and 50 minutes later, at a depth of just 500 meters, the shallowest significant event of the entire swarm. By the end of Tuesday, counted by Pacific Calendar Day, the catalogue held 27 located earthquakes for that day alone. Here is the first thing that is strange about this sequence. It got bigger as it went along. A classic main shock and aftershock sequence peaks immediately. The big one hits, and everything after it is smaller and less frequent as the fault settles. This one opened with 2 magnitude 3.2 events, ran for 4 days, and then produced its largest earthquake. That is backwards. That is the signature of a swarm, a sequence driven by something progressively loading the fault, rather than by one patch breaking and the neighborhood adjusting, and the pattern gets worse from there. Central California shakes constantly. To know whether 5 days of earthquakes means anything, you have to know what a normal week looks like in the same box on the map. Between the 1st of January and the 7th of August this year, 218 days, that box produced 313 located earthquakes, 1.44 earthquakes per day. That is the baseline. That is Pinnacles being Pinnacles. The swarm produced 59 located earthquakes in 6 days, 9.83 per day. The fault is running at roughly 6.8 times its own background rate. That is not a rounding artifact or a statistical wobble that disappears when you draw the box differently. It is a large, clean, sustained change in the behavior of a specific piece of the San Andreas over the better part of a week. There is one more thing to say about that number, and most coverage skips it. The catalogue is not the fault. A great many small earthquakes in central and northern California are recorded on instruments and never published at all. Detection algorithms have magnitude and quality thresholds. Analysts review a prioritized subset, and areas with denser instrument coverage simply publish more small events than areas with sparser coverage. So 59 is not a measurement. It is a floor. Whatever this swarm actually did, it did more of it than the numbers say. The second strange thing about this sequence is its shape. If a single stuck patch of fault breaks and then adjusts, you get a tight ball of earthquakes around one point. That is not what happened here. The activity resolves into three separate clusters spread along roughly 35 kilometers of the fault trace. The main cluster sits 4 to 8 kilometers northwest of Pinnacles, at depths between 300 meters and 5.5 kilometers. That is where the magnitude 3.94 in the overwhelming majority of events are. A southeast cluster sits 7 to 11 kilometers the other side of Pinnacles, deeper, 4 to 8 kilometers down, with magnitudes topping out around 2.5. It was active Saturday, Monday, and Tuesday. And a northwest cluster, up around Tres Pinos and Ridgemark, is deeper still, 6 to 12 kilometers, active Sunday and Monday. 3 clusters, 3 depth ranges, overlapping but not identical days. That distribution is far more consistent with something moving along the fault than with one stuck patch failing in place. And the depths point the same direction. One earthquake on Tuesday morning was located at a nominal depth of negative 2400ths of a kilometer, at or just above sea level datum, which in that terrain means effectively at the surface. That matters because the shallow upper crust on this fault is precisely the part that is supposed to be sliding freely. It is the part that cannot store elastic strain, and it is where the largest earthquake of the sequence nucleated, at 4.5 kilometers down. To understand why any of that is interesting, you need one number. The San Andreas fault, over geologic time, slips at 34 millimeters per year, give or take 3. That figure comes from both geologic mapping and satellite geodesy, and it is about as solid as anything in this field gets. It is the rate the plate boundary demands. The creeping section slips at 26 to 33 millimeters per year, right now, continuously, measurable, with instruments planted across the fault trace. Those two numbers are almost the same, which means there is essentially nothing left over. On a locked fault, the difference between the plate rate and the observed slip rate accumulates as elastic strain in the rock, and that stored strain is what a large earthquake spends. On the creeping section, that difference is close to zero. There's no strain bank. There's nothing to spend. That single arithmetic comparison is the entire scientific basis for calling this segment safe, and it is not a weak argument. It is the reason the official California hazard model, the third Uniform California Earthquake Rupture Forecast, was controversial when it included a through-going rupture crossing this segment. That branch was added by mathematical necessity rather than by evidence. Nobody had ever found a trace of such an earthquake actually happening. Paleoseismologists dug trenches across the central section, looking for ruptures that had broken the surface and found none in the last 2,000 years. So the case was closed, more or less, until somebody looked in a place a trench cannot reach. Before we go down that borehole, look at what the fault has already done at this exact location, because it is one of the most spectacular pieces of evidence in North American geology, and it is sitting right underneath the swarm. The rock spires that make Pinnacles National Park worth visiting are the remains of an ancient volcanic field, the Pinnacles Volcanic Formation. They are only half of it. The other half is the Neenach Volcanic Formation, and it sits near Lancaster in Southern California, on the far side of the fault. They were one volcanic field. The San Andreas cut it in two and carried the halves apart. The separation today is roughly 195 miles, 314 kilometers, accumulated over about 23 million years. That correlation was published by the geologist Vincent Matthews in 1976, and it remains one of the foundational demonstrations that continental scale strike-slip displacement is real, which is the context for everything that follows. This fault is not a crack. It is a machine that has moved half a volcano the length of California, and the part of it, under Pinnacles, has been chewing through moderate earthquakes on a generational schedule the entire time we have been watching. 1949, magnitude 4.7. 1951, 5.0. 1986, 4.8. 1988, 4.7. 1995, 4.9. In August of 2011, magnitude 4.64, about 600 meters from where Tuesday's earthquake nucleated 14 years and 11 months ago. By that record, a magnitude 3.94 here is unremarkable. 61 earthquakes of magnitude 3.5 or greater have been catalogued in this box since 1990, roughly 1.7 a year. Uncommon, but not rare and not unprecedented. Everything I have told you so far says this swarm is nothing. Now here is the part that does not fit. At Parkfield, at the southern end of the creeping section, there is a hole in the ground 3.2 kilometers deep that was drilled directly into the San Andreas Fault. It is called the San Andreas Fault Observatory at Depth, and it was built to answer what an active fault is actually made of. In 2022, a team led by Genevieve Coffey, then at Columbia University's Lamont Doherty Earth Observatory, published a study in the journal Geology based on cores pulled from that borehole. They analyzed a band of badly disturbed sedimentary rock lying between 3,192 and 3,196 meters below the surface. 4 meters of rock. The technique they used is the important part. When a fault slips in an earthquake, friction along the slipping surface spikes the temperature by hundreds of degrees for a moment. That heat chemically alters organic compounds in the surrounding rock, permanently. Measure how far the chemistry has been driven, and you can back calculate how much the fault moved, and therefore, roughly, how big the earthquake was. The method was developed by 2 of the study's co-authors, and had already been tested on faults in the northeastern United States, in Alaska, and offshore Japan. Those 4 meters of rock contained the signatures of more than 100 earthquakes, and in most of them, the fault moved more than 1.5 meters, 5 feet. Slip of that size corresponds to an earthquake of at least magnitude 6.9, the scale of Loma Prieta in 1989, or Northridge in 1994. The authors note that many of them could have been larger because the method for estimating magnitude from slip is still being refined. A second technique, potassium-argon dating, exploits the fact that frictional heat drives argon out of nearby rock and resets the radiometric clock. Those reset ages came back as young as 3.2 million years. That is an upper limit, not an age. It is the oldest they can be, not the youngest. Coffey has said publicly that some of these ruptures could have happened as recently as a few hundred or a few thousand years ago. More than 100 major earthquakes preserved in 4 meters of rock on the segment of the San Andreas that is not supposed to be able to produce one. This is where the story gets contested, and I want to give both sides properly, because the way this finding has been repackaged online is not what the researchers said. Coffey's own framing is careful. Her line is, "This means we can get larger earthquakes on the central section than we thought, and we should be aware that there is this potential that it is not always just continuous creep." Morgan Page, a seismologist at the United States Geological Survey and a co-author of the official California Hazard Assessment, put it more bluntly. She noted that the creeping section is a very difficult place to do paleoseismology in the first place, because the constant creep erases the evidence a trench would look for. And on the finding itself, if this holds up, this is the first evidence of a big seismic rupture in this part of the fault. Page also acknowledged the consequence that if a large earthquake can tear through the creeping section, it becomes possible, in her framing remote, for a rupture to start at the southern tip of the San Andreas, run through the middle, and continue to the northern end. That scenario is the one people mean when they say the big one. Then there is William Ellsworth, the Stanford geophysicist who has led research at the drill site, and his point is the counterweight. The viral version of this story leaves out entirely. His line, "Most earthquake scientists think these events happen rarely, because tectonic strain is not accumulating at significant rates along this segment, if at all, at the present time." Read that carefully, because he is not disputing the biomarkers. He is saying something narrower and more important. A fault releasing its strain by creeping is not, right now, banking the strain a great earthquake would need to spend. What the rock cores record is what this fault has done across geological time, under conditions nobody can reconstruct. Not what the fault is doing this month, which disposes of the claim circulating alongside coverage of this swarm, that a magnitude 3.94 at Pinnacles means the big one is coming. It does not. A moderate earthquake in a shallow swarm on a creeping fault does not measurably change the probability of a great California earthquake. Stephen Cox, one of the study's co-authors, said it directly. People should not be alarmed. Building codes in California are now quite good, and work like this exists to figure out what the biggest possible event is so everyone can prepare. Both things are true at once. This swarm is almost certainly nothing, and the fault it is happening on is not the fault we thought it was. To see why that matters in practical terms, follow the creeping section southeast to where it ends. Parkfield, California, is a town of about 18 people that is arguably the most heavily instrumented piece of ground on the planet. It sits exactly at the transition, the point where the creeping section hands off to the locked San Andreas. And it produced one of the most famous experiments in the history of seismology. Parkfield generated moderate earthquakes, magnitude 6 or thereabouts in 1857, 1881, 1901, 1922, 1934, and 1966. Average interval, about 22 years. That is close enough to a schedule that in the mid-1980s, the Geological Survey formally predicted the next one would arrive before 1993, wired the entire area with instruments, and waited. It did not come in 1993. It came in 2004, 38 years after the previous one, more than a decade past the outer edge of the prediction window, and when it finally ruptured, it broke in the opposite direction from the previous events. That failure is one of the most useful things that ever happened to this field, because it ended the idea that faults keep appointments. And it is the reason the borehole exists. If you cannot predict an earthquake by watching a fault from the surface, the next question is what the fault is physically made of. So they drilled into it and pulled out the rock carrying the record of 100 ruptures nobody knew about. There is one more reason Parkfield matters to the swarm. Slip in the middle of a creeping segment transfers stress to the ends of that segment. The northern end is San Juan Bautista, where the 1906 San Francisco rupture terminated. The southern end is Parkfield, where the fault locks up and continues into the Carrizo Plain, the reach that produced the Fort Tejon earthquake of 1857, an event estimated near magnitude 7.9. So any accelerated slip near Pinnacles incrementally increases the load at both terminations. I want to be precise about the size of that effect. It is tiny. It happens continuously whether or not there is a swarm, and no responsible reading of this data makes Tuesday's earthquake a trigger for anything. But the mechanism is real, and it is the correct answer to why anyone should care about a magnitude 3.94. And that leads to the inversion at the center of this whole story. While Pinnacles was producing 59 earthquakes in 6 days, the Bay Area recorded 11 in a week, essentially all below magnitude 2.1, with almost nothing on the northern San Andreas itself. Southern California produced nothing above magnitude 2.5 on the day of the swarm. A single magnitude 1.5 near the junction of the Garlock and the San Andreas, and little else. The southern San Andreas and the San Jacinto have been assessed at a 1,000-year stress high. The Coachella Reach has not produced a major earthquake since roughly 1680, 3.5 centuries of quiet on a fault that moves at plate rate. Now put those two facts side by side. 59 earthquakes in 6 days on the creeping section is strain leaving the system. 340 years of silence on the Coachella Reach is strain entering it every day without release. The part of the San Andreas that shakes constantly is the part that cannot hurt you. The parts that can kill tens of thousands of people do not shake at all. Seismicity is a measure of release, not a measure of danger. And the version of this story that treats a busy week at Pinnacles as a warning has the physics exactly backwards. There are 3 things worth watching over the next 2 weeks, and all 3 are answerable with public data. The first is whether this patch delivers something larger. The 2011 earthquake, magnitude 4.64, sits 600 meters from Tuesday's hypocenter, and this patch's history runs to magnitude 5.0. The sequence was still active at a reduced rate yesterday. Whether the magnitude 3.94 was the peak or foreshock to something bigger can only be answered looking backwards, but the catalogue will answer it within days. The second is the creep meter record. The most likely explanation for this sequence is a shallow creep transient, an episode where a stretch of the fault slides faster than its long-term average for days to weeks, loading the small stuck patches embedded in it and making them fail in order. That would explain the 4-day buildup, the spread along 35 kilometers of strike, and the shallow depths all at once. It is also testable. This segment has been monitored by creep meters and alignment arrays for more than 3 decades. If a creep event is confirmed for last week, the swarm has an explanation. If the creep meters show nothing, the alternative, a locked patch inside a creeping fault, keeping its generational schedule, gets stronger. The third is direction. That southeast cluster, 7 to 11 kilometers beyond Pinnacles, was active on 3 separate days. Whether the sequence stays where it is, dies out, or walks down strike toward Parkfield is the single most informative thing the next 2 weeks of catalog data can show us. One footnote before we close. 28 years ago yesterday, on the 12th of August, 1998, a magnitude 5.1 struck 10 kilometers southwest of Ridgemark, at the northwest end of this same system. That is a coincidence, and nothing more, but it is a reminder that the segment everyone has agreed to ignore has been busy the entire time. The creeping section is not a barrier. It is a description of how 150 kilometers of the San Andreas is behaving at this moment in geological time. 4 meters of rock from a borehole at Parkfield say it has behaved differently before. We will be watching the catalogue.